So remember, we're doing Riemann integration. So we've got a function defined on some interval from A up to B. And we want to work out the area under or the curve that's the definite integral that you know and love. And you can get and we've seen you can get a lower a series of lower Darboux sums. That's the area of rectangles like this. And you can also get an upper Darboux sum. That would be the area of rectangles that look more like this. And we've seen that the area of the lower Darboux sum, which is clearly less than the area under the curve, that's always less than the area than the upper Darboux sum. That's which is clearly going to be a little bit more than the area under the curve. So let's now talk about what the actual Riemann integral is. So here is our definition. So let's let f be a function from a closed bounded interval to the real numbers. And suppose, and we need this to be a bounded function. And then we let L of f, that is the supremum of the lower Darboux sums of f over any partition. And we're going to let U of f be the infimum of the upper Darboux sums of f, where P is any partition. Of our closed bounded interval from A to B. And it makes sense to talk about a supremum of the lower Darboux sums because remember, anytime you make a refinement, make a better partition. So here is one partition, and remember, anytime we refine it, anytime we take a better partition, we're going to get bigger, or we can't and to lose any area by taking smaller subintervals. That will only give us a bigger partition. And similarly, although the picture is harder to draw, so I won't try, the upper Darboux sum, if you take a refinement, if you take a better partition, you're only going to get less area. So the supremum of the lower Darboux sums, that's what gets you closer and closer to the full area under the curve. The infimum of the upper Darboux sums, that also gets you closer and closer to the full area under the curve. Now, I want to point out one fact, and this is that the lower Darboux sum of f is less than or equal to the upper. L of f is less than or equal to U of f. And this is because remember, every every lower Darboux sum is less than any other Darboux sum. So maybe this would be clearer if I use different letters for the partition, the two cases. This was part A4 of proposition 3.1.2, the last proposition we proved in the last video. So L of FP is a lower bound on the set of all upper Darboux sums. So L of FP is less than or equal to the greatest lower bound and that is true for all partitions P. So suddenly U of F is now an upper bound on the L of FP's. So U of F is greater than the supremum. It's greater than all of the L of FP's, so it's greater than the supremum of the L of FP's. Also known as L of F. Now let's go ahead and define the integral. So this is, here's the definition of Riemann integral from your book. So we start with a bounded function defined on a closed and bounded interval. And then we say that if the lower integral, L of F is sometimes called the lower Riemann integral, if the lower integral and the upper integral are equal to each other, then we say that F is Riemann integrable, and we let this thing, integral from A to B of F, that is L of F or U of F. This integral is only defined when L of F equals U of F, so we can use whichever of them we feel like. And we're going to let this notation, R bracket AB, be the set of all functions F defined on this closed and bounded interval such that F is bounded and integrable. So that's just, sometimes it's nice to be able to talk about the collection of integrable functions. Shorthand for F is in R of AB is a way of saying that F is integrable. Another example that we talked about is let f of x be the identity function, And then we saw it was painful. We showed that the lower sum of f over a partition was b squared minus a squared over 2 minus sum from j equals 1 to n xj minus 1 quantity squared over 2. And notice if we take xj to be a plus j times b minus a over n, then the lower sum of f over p is b squared minus a squared over 2 minus, then there are n terms and they're all of size b minus a over n quantity squared over 2. So letting n go to infinity, taking the supremum of all these f's, so we get L of f is b squared minus a squared over 2. And similarly, the upper sum of f over p is b of f, not over any, you take this infimum over all the partitions, you're going to get b squared minus a squared over 2. Again, and you're going to get the same error term except you add it and subtract it. So f is integrable. And the integral from a to b of f is b squared minus a squared over 2. So that's exactly the integration formula you no doubt remember from freshman calculus. We are eventually going to prove that continuous functions are indeed all integrable, which will make our lives much easier. We won't have to worry about that. But so here is the first step. Here is a proposition that makes it much easier to recognize when a function is integrable. So let's let f be a bounded function on a closed bounded interval. And then f is Riemann integrable, which you can also write as f is an element of this set of Riemann integrable functions on the interval from a to b, if and only if and then I'm going to put a star in front of this condition so I can refer to it by name. For every positive number epsilon, there exists a partition P of AB such that the upper sum of f over p minus the lower sum of f over p. Notice that that thing's never negative, and if f is not a constant, it's going to be positive. But the idea is you can find a partition such that this difference is less than epsilon. And let's prove this. So this is an if and only if, so we have to prove two directions. So we're going to suppose that f is integrable. So the infimum of the upper Darboux sums is the supremum of the lower Darbousums. This is also known as the integral from a to b of f. And we've made this argument many times before. The integral is the integral minus epsilon over 2. So we direct our reader to pick a positive number epsilon. Then this minus epsilon over 2 is not an upper bound. On the set of all L of all the lower Darbousums, because the least upper bound is bigger than it. So there is a partition Q, or I'll call it P, is such that L of Fp is greater than the integral minus epsilon over 2. And then similarly, there is a partition R such that the upper sum of f over R is less than the integral plus epsilon over 2. Now, P and R are not necessarily the same partition. However, we can work around that. So let's let Q be the union of P and R. Q is a partition of AB. Partition, remember, means a finite subset that includes the endpoints. P is a finite set, R is a finite set, their union is finite. P and R are both contained in AB, so Q is contained in AB, and the endpoints are in both P and R, so they must be in Q. And then by a proposition 3.1.2b, L of Fp is less than or equal to L of Fq. And I suppose this is also due to and upper sum of f over q less than or equal to the upper sum of f over r. So this difference u of fq minus L of fq that's less than or equal to u of fr minus L of fq. Yeah. So we write u of fq minus L of fq less than or equal to u of fr. Now I'm going to go ahead and subtract off that integral, and that's okay because I'm going to add it again. And then this first difference here that is less than epsilon over 2, and so is this second difference is also less than epsilon over 2, so this is epsilon. So the condition star is true. Now the converse. Let's suppose star is true. We're going to pick epsilon greater than 0 and let P be the partition given by condition star. Then L of Fp, that's less than or equal to the supremum of all the L's of Fp, so that's less than the lower Riemann integral. And we said above that was less than or equal to the upper Riemann integral. Actually, we don't really need that. We just need that the upper Riemann integral is less than or equal to this particular Darboux sum. So then we write U of F minus L of F. Suppose we do in fact need that the upper Riemann sum is bigger. We would like this thing to note that this thing is not negative. That's less than U of F P E minus L of F U of Fp minus L of Fp, which is less than epsilon. So U of F minus L of F is less than epsilon for all epsilon. So that must mean that U of F is equal to L of F, and that means F is Riemann integrable. And that completes that direction of the proof. As a corollary to this lemma and the problem I've assigned on your homework, if F is a function on a closed bounded interval to the real numbers, then F is continuous then F is Riemann integrable. So all continuous functions, at least on closed bounded intervals, are Riemann integrable. And I will note that you won't even need to assume that F is continuous is bounded by the extreme value theorem. F is bounded. And by your last homework, if epsilon is greater than 0, there is a partition P of our interval with the upper Darboux sum minus the lower Darboux sum less than epsilon. So by the proposition we just proved, f is Riemann integrable. The next thing I want to prove is, well, ultimately I want to prove that if you chop up an interval, you can integrate over the pieces. This is the result that I'm sure you know. Integral from a to b is the integral from a to c plus the integral from c to b, but we are going to prove this in pieces. So here is a lemma. Let x, we'll write that as x naught less than x1 less than up through xn. Let that be a partition of an interval from a to b of a closed bound interval. So here's two things. If Q is a refinement of X, and Qj, that's xj minus 1, xj intersect Q, then Qj is a partition of this interval, and also Q is the union from j equals 1 to n of Qj. Conversely, if Qj is a partition of this interval, and if we let Q be the union of the Qj's, then Q is a refinement of X. And conversely, Qj is equal to the intersection of Q with this interval. What am I trying to get at here? Here's my number line. Here's my interval from A to B. Then here's my partition X. I get the points A and B. I also get a couple of points inside somewhere. And then here is, and then Q1, either I start with Q1, here's Q1, Q2, I would have to repeat that point. Here is the picture of what I'm trying to get at. So either I start with Q, which is a refinement, and then I grab it Q1, and then I break it up into pieces Q1, Q2, Q3, or I start with Q1, Q2, Q3, I put them together, I get one partition. There way. We can go either way. And so furthermore, in either case, the upper Lebesgue sum of f over q, that's the sum from j turns out to be the sum of the upper sum of f over qj, and the lower sum of f over q, it's the sum of the lower sums of f over qj. I suppose I had better specify that this is true if f is a function defined on our interval that is bounded. And you can ask me about this lemma in class if you're confused by it. I think we will not write out a detailed proof. It will be a lot of technicality for not a lot of gain, and it should be pretty clear just from the picture what is going on. And we see that it should be pretty clear that you can build refinements out of smaller refinements or break up refinements over subintervals, and then just the upper sum of f over q, you would be taking the supremum over this interval, this interval, this interval, this interval, this interval. Whereas with the sum, you would first add these three together, then you'd stop, then you'd add these three together, then you'd add the supremum on these three together, and then put them together. Regardless, you're adding up over the same sets of intervals. So we'll stipulate that the lemma is true. So here is the next proposition. This is really the reason we went through that lemma. So let's let f be a bounded function on a closed bounded interval. Let's let x be a partition of the closed bounded interval. So x is really a set. It's a set of finitely many points, including A, including B, and all the other points are between A and B, and we're just saying we're going to number them in order, x naught being the smallest one, which is A, xn being the biggest one, and which is B. And then f is Riemann integrable on the entire set if and only if f is Riemann integrable on each of the little intervals and if it's integrable on all those intervals, we can actually say something about the integral. The integral from a to b to f, it's the sum from j equals 1 to n, integral xj minus 1 up to xj of f. So let's prove this. So first off, we're going to suppose that f is Riemann integrable on this interval, and then we pick a positive number epsilon, and we let p be a partition with the upper sum of f over p minus lower sum of f over p. This is a partition of the interval from a to b. So upper sum minus lower sum less than epsilon, and by proposition 3.1.4, p is going to exist. Now we're going to let Q be. It's a refinement of p, but it's also a refinement of x. So by proposition 3.1.2, we have that the upper sum of fq minus the the lower sum of fq, that difference less than or equal to the difference with p's, because q is a refinement, so that is also less than epsilon. Now if k is between 1 and n, then we can write upper sum of f over the partition qk. Qk is as in the lemma. Let's subtract off the lower sum of f. Then that's less than or equal to, if we take all of these upper and lower differences, because the upper sum is always bigger than the lower sum. So just taking one of these things we're adding up, that can't be any bigger than taking all of them. And then by the lemma, this is equal to the upper sum of f over q minus the lower sum of f over q, which is less than epsilon. So, but a proposition 3.1.4, f is Riemann integrable on the interval from xk minus 1 to xk for all of those k. Then conversely, let's suppose f is Riemann integrable on each of the little intervals. And then we grab a partition of each of the little intervals with the upper sum minus the lower sum less than, this time we'll make it epsilon over n. We can do that. Epsilon over n is a positive number. Then if q is the union of the qj's, then q is a partition of this interval from a to b, and the upper sum of f over q minus the lower sum of f over q that's equal to the sum over the qj's of the same upper sum or lower sum or difference, which is less than epsilon. So f is Riemann integrable on the entire interval AB, and again using proposition. So we've seen that if we're integrable on the little interval then were integrable on the big intervals. Now we just need to see that the integrals match up. So let's let P be a partition of AB, and we'll let Q be the partition that's a refinement of both P and X. Then the upper sum of F over P, going to a refinement, more points just makes the upper sum lower. And that's the sum from j equals 1 to n, upper sum on the QJs. And then we remember that the integral from xj minus 1 to xj of f, that's the infimum of all the upper sums over partitions of qj over partitions of this interval. So the upper sum is bounded from below by the interval. Qj is the intersection of q with xj minus 1, xj, as usual. And then we take the supremum, the infimum over those p's. So the integral from a to b of f, that's the infimum of the upper sums. But each of these guys individually is at most the sum of the intervals on the little intervals. And then similarly, the lower sum of f over p, take a refinement, you get your lower sum only gets bigger. Then we apply our lemma again. And the lower sum is always less than the integral. So the integral is the supremum of the lower sums. And then this, I missed a sum of little integrals. That's an upper bound on the lower Lebesgue sum for any partition. So we've got a two-sided inequality. So we must have that you can break up an integral into integrals over smaller intervals. And that completes the proof.